So in the last two videos, we have done the basic of linear algebra and we have gone with vector spaces and field. Now in this one, we will go with the matrices one. So in the matrices, as we know, with the multiplication of matrices, the number of rows of the first matrix and the number of column of the second matrix should be same. Like we have to multiply the 2 by 2 matrices and 3 by 3. So we can't multiply this because the number of column in first and the number of rows in second are not same. The basic information for multiplication, I assume that you know it already. So in this video, I will just go with the vector addition and the multiplication of the matrices. So m multiplied by n, and let's assume we have a matrix of 2 by 2. It's 2, 4, 6, 8. So if we want to add some another matrix of 2 by 2, we have 1, 3, 9, 7. So we have to just add the columns of 1 by 1 matrices with 1 by 1. It will be 2 plus 1, 4 plus 3, 6 plus 9, 8 plus 7. Same with the multiplication. If we have to multiply something with the matrices, we have to multiply with each of the number of elements. So for vector addition, we can just multiply if they have the same number of rows and same number of columns. And for scalar multiplication, the number of column of first matrix should be equal to number of rows of second matrix. Now we can just jump to the vector spaces, the new topic. We will go with the definition first. A vector space over a field F is a set to V together with vector addition and scalar multiplication operations. Such that for all A plus B, C vector and Rx belongs to F, the following properties hold. So as we seen in the field, there are certain axioms we have to be sure if we have to say some set of field. For the vector space, it's the same thing. It's a commutativity. I already explained all this property in the field one, so I will not go with them again. Associativity, additive identity, additive inverse, multiplicative identity, distributive distributivity, and multiplicative associativity. If we have all these properties hold for some vector space, then we can say that it's a vector space over a field map. Now we will go with some of the basic remarks for this chapter. So the elements of V are called vectors. Elements of F field are called scalars. When we have field is equal to the set of real number, we can call V a real vector space. For the vector space, we can do some examples afterwards to understand it properly. If the field is a set of complex number, we can say the V is a complex vector space. Now we will go with some basic theorems. We are not proving any theorems right now. We are just going with them. The first theorem is for each positive integer n, Rn is a vector space over R. We have gone with the Cartesian space. This is for the real number. Rn is a vector space over R. So R is a set of all the real numbers. So this theorem basically proves that for each positive integer n, Rn is a vector space over R. So if we have some example asking what is the vector space over R, you can say lots of different number R1, R2, R3. It's a like basic knowledge. Then we go with the next theorem. It's for the polynomial. So I'll say for each positive integer n, Pnr is a vector space over R. It's for the polynomial one. We already go with the polynomial before. Now we will go with the matrices. Say let m and n be two positive integers m m and r is a vector space over R. So first we go with the vectors. Now we are going with the vector space. So we will go with three things in this chapter: Cartesian space, polynomials, and matrices. Now, as we go, we know real number before, but now we will go with some basic knowledge of complex numbers. Just give me a minute. So for the complex number, assume we have a basic knowledge about the complex number from your previous math courses, but I will go with some basic things. Definition. A complex number is an ordered pair A comma B, where A comma B belongs to real number. We can write complex numbers as that and A plus IB. The complex number I square is equal to -1. So I will be equal to root of minus, square root of minus. The complex number, we have a basic thing calling a real part of Z, which is RA, and RB is an imaginary part of Z. And our I is iota. So for the writing the set of complex number, we can write C is equal to A plus IB. AB belongs to real number So this is our set of a complex number. In complex number, the another basic idea is we can go with a Cartesian plane. So in that we will assume A is equal to r cos theta and B is equal to r sin theta. If we want to write the complex number into the polar coordinates, we will go with r cos theta plus I r sin theta. Taking r into common, we will get cos theta plus I sin theta. Here we will call our r the modulus and theta is equal to the argument of z. So how we will find the r? So our r will be equal to the modulus of z will be equal to a square plus b square root. So this is our modulus. Now for the conjugate, denoted by z with the bar on his head, and we can find it by a minus iota b. Now we will go with the addition and multiplication of complex number. Let us assume with an example that we have a z complex number. We can write it by real number and imaginary part formation. We have another complex number w with c plus id. So if we have asked z plus w, we will add the real part together and then we will add the imaginary part together. With the multiplication zw, we have a plus ib multiplied by c plus id. We will go with the distributive property ibc plus I. So it will be ac plus iad. This will be ibc. This will be I square bd. So as we know, I square is equal to minus 1. So we can write the minus 1 there. It will be AC minus BD plus I AD plus BC. Now we will go with the properties of complex. So let us assume we have Z and W be the complex number. We can write when we add the complex number with the conjugate of the complex number, we will get 2A, the real part of this. We can write them as REZ2. We can denote A is equal to REZ and B is equal to IMZ, imaginary part and the real part. The another property for the complex number is when we multiply the conjugate with its complex number, we will get the square of its modulus. What is the conjugate of the addition of it? Like we have this conjugate, we can write them differently too. And for the multiplication, it's just the same. So it will be same if we multiply and then find conjugate, and if we find the conjugate of individual first and then we multiply. So what is the conjugate of the conjugate itself? It's the same complex number again. The another property of it is that the real part of the conjugate, the real part of the complex number should be less than or equal to the complex number itself. Same with the B thing. The real part of the imaginary part of complex number should be less than equal to the complex number itself. The modulus of the conjugate of the complex number should be equal to the modulus of the complex number. The modulus of the multiplication of conjugate number, you can write them individually, the modulus, and then you can multiply. The last property of the complex number that the addition of the two complex numbers should follow the triangle inequality. That means the addition of conjugate number should be less than and equal to the addition of the two individual part of the complex number. Here we can finish the complex number thing. In our next lecture, we will go with the vector space thing more with an example and can go with the different topics too. Thank you.